Right, since we've been talking about the mole since I brought it up earlier, this is for an individual formula unit, so, which means just one ammonium and one nitrate. But if I had a mole of formula units, well, if I had a dozen, you know, it'd be 12 times this mass, right? But if I had a mole, it would be 602 million trillion times this mass in U, which would give me an odd number, right? But then if I convert U to gram, then it gives me a very simple and interesting number. If I convert U to gram, then it turns out that there's going to be 80.06 grams for a mole of formula units. 80.06 grams. And so this is very useful. So we can do it. And we interchange these all the time. We either think in terms of U per individual molecule or formula unit, or grams per mole of formula units, or per mole of molecules. And I'll talk about the mole next. So these are some examples here. What are they using? Are they using the average or the yeah, they're using the average. These are the numbers we've memorized, right? The 2 decimal places. 1600 means what? The red must be, and the black must be carbon. And so the average mass of a CO2 molecule is, yeah, 44.01. That's the average. If I had a mole of those CO2 molecules, how much would it weigh?
44 grams.
Yeah, 44. Good. All right, what we're going to do is, this is the formula mass of ammonium nitrate. Same thing. 80.0. How did they get that? They got that because of hydrogen. You see the hydrogen they're using? I didn't do that. It's all right. We can expect a little bit of round off error. Their answer is a little bit more accurate. Their answer is a little bit more accurate, but the reason I have you do hydrogen to 101 is for speed. Because let's say you're taking a time test, then you want to be able to calculate these things, these masses, very rapidly. And so you can calculate them much faster if they're all to 2 decimal places. You have to go to 3. When must we use this? 1008. When must we use 1008? When we're calculating the mass of something like H2, you know, how much does an H2 weigh? If you use 101, then it's 202. It's double that. That's only 3 sig figs. We want 4 sig figs. So if we use 1008, then we'll double that, and it comes out to 2016. So that's what we use. Or if we're dealing with a single hydrogen, how much does a single hydrogen atom weigh on average? Would you say 101 or would you say 1008? You'd say 108, so we got 4 sig figs. Why do we need 4 sig figs? We need 4 sig figs for all our calculations. All our calculations, we want that. And so I could have saved time here because I wouldn't have to do this round off. I wouldn't have to do the more complex addition. You know, just do decimal. I could do it in my head easily.
Can we do 1008 anyway? Like,
Yeah, if you want to, yeah. No, not at all. Not at all. If you want to do 108, that's fine.
Okay.
Some people do 10079. You can do that too. All right. Well, before I get to moles, I want to revisit this because we're going to talk about this at the end. If I want to do percent by mass by mass, then I need to know how many U of nitrogen or grams of nitrogen I have. You know, in this case, you know, I could just do grams. You know, if this were 2 atoms of nitrogen, then it weighed 2802 U. But if this were 2 moles of nitrogen, how much would it weigh? 28.02 grams. So we could just say 28.02 grams of nitrogen for what? 100 grams of total? How many grams total? No, it would be 80.06 grams total. You know, this is the grams of ammonium nitrate. And so out of that 80.06 grams of ammonium nitrate, 28.02 grams of it is nitrogen. And then we'll just times it by 100%. Times it by 100%. Then you know, people who are into gardening are much more interested in the nitrogen content in grams.
And so let's go to 28.02 divided by 80.06 times 100, 34.99. 34.99 sub 8% nitrogen by mass. If I did this by mass, this would be what? MM? MV? VV? What would this be? Percentage. This would be an MM. And then, well, what about atoms, you know? Well, you know, for atoms, we usually just write MOL with a percentage. It's normal stuff. All right, so yeah, it's quite a bit different because the atoms weigh different amounts, you know, but for, you know, so in some cases, knowing the percent by mass is very important. In other cases, it's not as important, but the atom ratio of the atom percentage. All right, so what is the definition of the mole? So let's talk about that now. So this is what we need to know. The mole, M-O-L-E, abbreviated M-O-L. Amount of any substance that contains the same number of units as the number of atoms, 12 grams of carbon-12. Avogadro's number. One thing is, how many sig figs are we doing for most of our calculations? 4. And so this is not enough for Avogadro's. This is okay for Chem 4, but when you get into Chem 1A, you don't want to memorize this number. You want to memorize this number. This is called Avogadro's number. And this is for the mole. Avogadro's number is abbreviated to capital N sub A. And we memorize it to 4 sig figs. This is not exact. This is 4 sig figs. It's 0.022 times 10 to the 23rd. Now, where does this number come from? In other words, how is it defined? How's this number defined? If you wanted to reproduce this number, let's say, I need 5 sig figs. I'm doing a more precise calculation, more accurate calculation. I need it to 5 sig figs. Where does the number come from?
The number of units and 12 grams of carbon-12.
Yeah, that's so weird. That's the way it's stated there. Where this number comes from is this. Let's take a look at one carbon-12 atom, or nuclid. Nuclid is when you're looking at a specific isotope. So for example, if you're looking at carbon-12, rather than calling it a carbon-12 atom, we'll call it carbon-12 nuclid or isotope. The isotope or atom of that specific isotope. So what's easier is just say nuclid, atom of that specific isotope. How much does a carbon-12 atom weigh? How much does a single carbon-12 atom weigh? 12 U, only 2 sig figs?
12.01.
12.01? 12.01 is wrong. Wrong. Why? Yeah. Or more specifically, 12U is carbon-12 is defined. This is by definition. Exact. Okay, why? Because somebody decided to define it that way. That's exact. All right, so now let's get exactly 12 grams of carbon-12. How you get it, we don't care. This is all hypothetical. Now we'll get
let's get exactly 12 grams of carbon-12. And then determine approximately how many carbon-12 atoms are contained. And so here we have pure carbon-12, and we have exactly 12 grams. And then we want to count the number. Count the number. Well, are we really going to count the number? Sit there and count? No, but we're going to calculate and figure it out based on chemistry. And it turns out the number of carbon-12 atoms equals 6.022 dot dot dot. It keeps going times 10 to the 23rd carbon-12 atoms. So that's a terribly inconvenient number. So we'll just call it the mole. And the number itself is called Avogadro's number. And so, in other words, determine, well, how many atoms? There's a mole's worth of atoms. That's how many atoms. A mole's worth. In fact, exactly a mole's worth of atoms. Well, how many is a mole? A mole is approximately 6.022 times 10 to the 23rd atom. And so if we define Avogadro's and the mole in this way, then there's a parallel relationship. And the parallel relationship is this. We have molecular mass. So this is the relationship there. The reason it was defined in this funny way, because why didn't they just pick a simple number to remember? A simple number would be 1 times 10 to the 20th. 1 times 10 to the 20th, you can see that. They didn't pick a simple number to remember because it would destroy this relationship. The relationship is molecular mass is going to be U per molecule. That's molecular mass. And then we have formula mass. Formula mass or formula unit mass would be U per formula unit. Okay. And so numerically, this is going to be the same as what we call the molar mass. The molar mass is just a generic term, which is going to be grams per mole of molecules or formula units. And numerically, they're going to be the same. Same number. So that's the relationship. And so when we see that number, we read it in two ways. What's the average mass of carbon? 12.01 U per atom, or 12.01 grams per mole of carbon atoms. So I need to add that in here, atomic mass. Atomic mass is going to be U per atom, or in terms of molar mass, it would just be grams per mole of atom. Molar mass is used for these three things. It could be grams per mole molecules, it could be grams per mole formula units, or it could be grams per mole of atoms. Molar mass is just used for these, but it's never used for the molecular mass. People confuse molecular mass and molar mass all the time, but they're totally different numbers, totally different things. So these are the same. Numerically, they're the same. A sample consists of 0.25 moles of ammonia. How many ammonia molecules is this?
And so we're going to have some additional conversion factors with this. The conversion factors that we're going to have is we're going to have moles to grams or grams to moles using the molar mass. We're going to have moles to units. You know, how many individual units do we have? Or units to mole. Units would be formula units, molecules, or atoms. And we're going to use Avogadro's number for this. And so we're going to use these in dimensional analysis. Like in this particular problem, we have 0.25 moles of ammonia. What's the formula for ammonia? NH3. Is there a charge? No, there's no charge. So 0.25 mole. And so here we know this. We can cancel out the moles because 1 mole of anything is how many of those things? Like 1 dozen of anything is how many of those things? 1 dozen would be 12. 1 mole would be 6.022 times 10 to the 23rd ammonia. Now, is this molecules or formula unit? Well, in this case, we could say molecules because ammonia actually forms molecule. We could say molecule. And so it's going to be 1/4 mole. What's a 1/4 mole? Let's calculate it. Sub 0 times 10 to the 23rd ammonia molecule. See what they got. So here they just did the same thing, just using this conversion factor, Avogadro's units per mole. Ah, interesting. They never did this before. They always rounded. This time they didn't round it. So we must have somebody else making the PowerPoint, not the usual author. The normal author would have rounded this one immediately to 1.5. Did you notice that? All the earlier PowerPoints, or they're just inconsistent, but it's hard. You know, you're consistent for 6 chapters, and all of a sudden for chapter 7 you change. Well, anyway, this is too many sig figs, of course. We're only allowed 2. Here's the parallel relationship, you know, what we're talking about. Atomic mass. 1 carbon-12 atom weighs 12 U. Molar mass. 1 mole of carbon-12 atoms weighs 12 grams. It's a parallel relationship, but it's funny written in this way because to me it doesn't really make that much sense the way they wrote it. Calculate the mass of calcium fluoride. Well, first off, we got to get the formula for calcium fluoride. What do you think, ionic or molecular? Ionic or molecular? Well, if you have a metal, calcium's a metal, and a non-metal, then they're typically not molecular. They're typically ionic. And so what's the calcium ion? What's the charge on the calcium ion? C, what's the symbol for calcium? CR? Ca? Charge? Fluoride? Negative. Okay, so we need 2 fluoride to balance out the 2 plus, so CaF2. Now, we got to go to the periodic table, so go to the periodic table here. nitrate of calcium first. All right, what are we gonna do? Should we go 3 decimal places or should we go 2? Well, I have 2 digits here. And so if I go 2 decimal, that's gonna give me 4 sig figs. The fluorine's the same kind of deal. So I'm only gonna go 2 decimal and I'm gonna round it, which is gonna lead to round off error. If you don't want a round off error, you want a little bit more accuracy, then don't round it. But how many calciums do we have? 1. Okay, now this one, you know, I'm a stickler for writing units, so I'm gonna round this to 40.08. The only reason is for speed, because sometimes you want to do these in your head and not use a calculator. But I'm not gonna put the units here because we have 2 units that we could choose from. This would be, tell me the 2 units. U per Yeah, but be more specific. You're right, it is per formula unit, but be more specific. Is the formula unit a molecule? Is the formula unit a, empirical unit, or is the formula unit a atom? Atom. So this is U per atoms. Or it would be grams per mole of atoms. So, so therefore we could leave the units off and then add them later. And then 2 fluorines is going to be 2 times. Now fluorine, which we only use for the mass for fluorine. So let's go swing over. Fluorine I don't have memorized because it's a lot less common. But we're going to go 2 decimal places. So what would you do this to? 19.00. So I'm not going to even write the units here. We're just going to go, okay, this is 40.08 plus 19 times 2 is 38. Is that right?
Yeah.
0.00. That gives me 8087. 7808. Okay, and then we have 2 choices of units. Now, well, this would be grams per atom, or what is this?
Grams per mole.
Grams per mole of what? Molecule? Grams per mole of molecules?
Mole.
Moles of what? Calcium fluoride what? Molecules? Calcium fluoride molecules? Calcium fluoride ions? Calcium fluoride's made up of ions, but it's an ionic compound. We call it a compound. Does calcium fluoride form molecules, or does it form what? What else? It forms an ionic lattice, so we shouldn't call it a molecule. We should call it moles of formula units. Or this would be U per formula unit. We don't use molecules. All right, what did they get? They got the same thing, 7808. But they automatically, hey, look what they did. They just wrote grams per mole. Why am I asking you to put down more than that? Yeah, the reason why I'm asking you to do more than that is so you can avoid making simple errors. Simple errors like on the last, we'll talk about the last test. Yes, I think we could talk about the last test right now. So let's say I wanted a 0.5 gram of, what was that? 0.5 gram of carbon monoxide? Is that it? What did I ask for on the last test? 0.5 gram of gold, right? 0.5 gram of gold. How many gallons of water would it take to recover 0.5 gram of gold from the ocean? Do you remember that? Do you know how many people did this? They wrote 0.5 gram and then they canceled out the gram.
Oh, was it lead? Was it lead in water? All right. It was a half a gram of lead. They did this. Not just one, but a lot of people did this. What's the wrong problem with this? This is grams of lead. This is grams of water. How can half a gram of lead cancel out 1 gram of water? Does it make sense at all? When I saw this makes absolutely no sense to me. And this is like, you know, but I can see it's an easy error, you know, if you aren't being specific enough. And so a lot of people made that error. But I'll tell you, you know, if you continue making that kind of error, you aren't going to get that far. You got to be more exacting on this, because the calculations just get harder as we go along. So this is why, even though it's not required now, pretty soon you're going to need to know this. Otherwise, you're going to have mistakes like that, and people are going to look at it right away and say, "Oh, wrong, totally wrong." So actually, a mole of what? It's like a dozen. You know, a dozen of what? What do you call it? A dozen eggs? A dozen cars? You know, and so you might say, okay, that is 1 kilogram per dozen. You go, what the heck is a dozen of what? A dozen feathers weighs 1 kilogram? You know, that's the kind of thing that people are going to see when they see something like that. But most of the time you're okay, like 90% of the time you're okay not writing what it is, and you'll be okay doing the calculation. But that 10% or that 5% or that 3%, you're going to be in trouble, you know. And you can get by, and lots of people do, but eventually it catches up. You know, once you hit a certain level, you can't get by. So let's do that here. Iron, Fe. The average iron is 55.85 grams per mole of atoms. And so how many, this is 602 million trillion atoms here. It doesn't take up that much volume, right? This is 26.98 grams per mole for aluminum, but it's going to be moles of aluminum atoms. The same thing, mercury. This is a mole. And so when you look at 602, if you look at nitrogen, there's 602 million trillion nitrogen molecules, or what is it? 602 million trillion atoms, 602 million trillion molecules, or 602 million trillion formula units? Which one would be the most descriptive? For this one, molecules. All these are going to be atoms. Now let's go over here. This is going to be 249.70 grams per mole. Remember this is the pentahydrate?
Yeah.
And so what should we say? Is this a mole of molecules here? This is a mole of formula units. So if I had a mole, that would mean how many copper ions would I have? And do you know, are those copper 1 or copper 2 ions? Can you tell?
Copper.
These are copper 2 ions. How many copper 2 ions are present here? 1 mole, right? If I have a mole of these, then I have a mole of coppers, and I have a mole of sulfates, and I have how many moles of water? 5 moles of water. Although it doesn't look like 5 moles of water, it's there, but there's 5 moles of water. So they're just sucked in. 5 moles of water, let's say 20 grams, that's about 100 grams of water that gets sucked into the crystals. Do you remember the hydrate versus the anhydrous form? So it's like it balloons up. It's got to balloon up or something, you know, to accommodate it, but it doesn't really balloon up that much. So this is a hydrate. This is mercury 2 oxide. What do you think? Is that ionic, molecular? What is that? That's going to be ionic. So this would be 216.6 grams per mole of formula unit. Okay, now we're at water. This should be 18.02 grams per mole. This is, well, a gram of water is about a milliliter. So this is 18.02 milliliters of water. And that's going to weigh 18.02 grams, which contains a mole of water molecules. This is oxalic acid. Is oxalic acid ionic or molecular? What would you say? It's more, you would think it's ionic because you got the hydrogen ion and the, in this case, oxalate ion. But we consider it kind of in the borderline between ionic and molecular. And so typically we think of these as molecules, molecular. You know, that reminds me of HCl. You remember HCl? What two names did we give it? Hydrogen chloride gas. The hydrogen chloride gas consists of HCl molecules in the gas phase. Or we called it hydrochloric acid. Hydrochloric acid, actually those molecules break apart in water to form hydrogen ions, aka hydronium, and chloride ions. And so that's the origin of the difference in the nomenclature. So something like HCl gas, it's hydrogen chloride. And then you dissolve it in water, you call it hydrochloric acid. Well, this is not dissolved in water. This is a solid acid. HCl is a gaseous acid. Oxalic acid is a solid. This is pure oxalic acid here. And it's going to be 90.04 grams per mole of molecules. This is molecular. And this is the dihydrate. So for every molecule of oxalic acid, we have 2 moles of water. I mean, two water molecules. For every mole of oxalic acid molecules, we have 2 moles of water. And so just some additional. This tells you about how much. So mole, you know, typically we work with 1 mole or part of a mole or several moles. And so today you're probably going to drink more than 1 mole of water, I hope, right? Sure. Otherwise, you'd be dehydrated. You're carrying out a laboratory reaction that requires 0.0360 moles of barium chloride. How many grams of compound do you measure out? And so the first thing is, what the heck is barium chloride? Is it ionic or molecular? Ionic. Okay, so we got to figure out what is the barium ion? Ba charge. Okay, B would be fluoride, but barium is located in the second column. And so this would be Ba2 plus, and then fluoride. So we need 2 of those, so BaCl2. So let's get the mass of barium here. The second column, do you know what name we give the elements in the second column of the periodic table? Yeah, the first column is called the alkali metals. The second column is called the alkaline. Yeah. So if we look at barium, it's near the bottom. Somebody asked me about imaging agents for CAT scans, right? For CAT scans, I actually had a couple of CAT scans done. The first time I had a CAT scan done, I took barium. Have you ever heard of barium cocktail? I drank a barium cocktail, which is, I think it was barium sulfate. Barium's pretty toxic. Sulfate's not as toxic, but barium's pretty toxic. The thing that made it, it was like a paste of barium sulfate. And so it's hard to digest that paste. In fact, your stomach acids really don't break it down. If your stomach acids broke down the barium sulfate into barium ions and sulfate ions probably aren't going to cause much damage, but the barium ions will cause damage. You know, it's toxic.
So I drank some barium sulfate, and then they hit me with X-rays, and they were able to image me. I forgot what they were looking for. What's that? It tasted, you know, like medicine, but it was not terrible, but it was not good. They put some kind of cherry flavor in it, I think, which is not good. But it was okay. I mean, it wasn't the worst. The second time I had it, I took iodine. I think it was potassium iodide or iodine. No, it was iodine. Iodine. I had a reaction to it, allergic reaction to it. And so I'm probably gonna, if I do another one, I'm probably gonna go back to barium sulfate, which surprised me because I didn't think I was allergic to iodine because I've used like betadine and like a tincture of iodine as a disinfectant before. Never had a reaction. But, you know, I had to drink a lot of iodine. Now, why barium, why iodine? Well, you know what works really good at absorbing X-rays? Lead. But do you want to drink a lead cocktail?
No.
No. You don't want to drink a lead cocktail. And so, well, what are the alternatives to lead? Well, barium and iodine, because barium has a lot of electrons, like lead, and iodine has a lot of electrons. You know, they're down low in the periodic table. I mean, take a look. Barium has how many electrons? 56. You know? Iodine has fewer. You know? It has to do with the electrons. You know, lead is great at absorbing X-rays. Lead's 82. 53 for iodine. I guess we could take some of these other metals, but, you know, probably issues with that. Like osmium and iridium are very rare. Platinum, I guess if you have a lot of money, you could do a platinum or gold cocktail. I don't know if those would be effective. You definitely do not want to do a mercury cocktail. That wouldn't be so good. All right, so let's go back to this. Barium is, well, what is the mass of barium?
137.33.
Yeah. So we've got 137.33, and then chlorine. Actually, chlorine I have memorized too, 35.45. Chlorine's pretty common. Since it's common, I can remember it. And two of them are very common, so 70.90 and 137.33, which gives me, well, let's see, gives me effort to save time. 208.2. Huh. I don't know what they're doing here. You know, this to me is kind of dumb. You know, why didn't they do 137.33? Why do this extra rounding step? Does that make sense to you? Does this look kind of, yeah. And so, you know, keep it to 2 decimals. You're going to save time rather than doing this. I know why they did it. Do you know why they did it? Because they wanted 4 sig figs. But since we're doing addition, I'm more interested in not sig figs. I'm more interested in decimals. Anyway, why do we want this? Because we want our conversion factors to have a minimum of 4 sig figs, because usually what they're going to give us is 3 sig figs. Have you noticed that?
Yes.
Yeah. And so that, therefore, we want to minimize round-off error. We minimize round-off error by using more sig figs in the conversion factors than what we're given. And so they're doing 4. Well, I like that idea too. I like that thinking. And so here we have 0.0360 moles. Moles, well, it's going to be 208.2 grams of barium chloride per mole barium chloride. Molecules or formula units in this case? Does barium chloride form molecules or does it form formula units?
it forms ionic compounds, so it'd be formula units.
Formula unit can be used for molecules as well, but it would have to be used for ionic.
All right, so this is a typical dimensional analysis problem in this chapter. A typical one is starting off with a number of units. We can go from units to moles using Avogadro's number, moles to grams using the molar mass, mMs for molar mass, n to the base for Avogadro's. Or we can convert grams to moles using the molar mass, and then moles to units using Avogadro's number. And so those are some typical conversions. These are paths that are commonly encountered. The paths that's commonly encountered. Yeah.
What is MM?
Molar mass. Molar mass is grams per mole. Always grams per mole of whatever. What's the molar mass? This map we're going to redraw. You don't have to worry about it. This map I'm going to skip entirely. Determine the mass in grams of 3.2 times 10 to the 24 molecules of sulfur tetrafluoride. Well, sulfur tetrafluoride, this is definitely molecular because of the naming system, you know. And so what is the formula for sulfur tetrafluoride? SF4. It's SF4. And so S is going to be sulfur. Sulfur is 32.066 according to our periodic table. We have to be careful here because we want to be consistent with our rounding. You know, because when we round, we want to be consistent with our rounding because sometimes you round up, sometimes you round down. And to minimize it, you want to do it. So did they round this correctly for sulfur? No, they didn't round it correctly. It should be 32.07. Should be 32.07. But that's okay. Oh yeah. So I would have used 32.07. They used 32.06. And I hate this here because this doesn't tell us how many sig figs. When I see this, it looks like 2 sig figs. If I saw this on your paper, I think you're thinking 2 sig figs, which is wrong. And so automatically I think you did it wrong. And so I would write this as 19.00. And then I don't like this either because, you know, we're doing it by decimal places. So I'd like to do the calculation and then add them to make sure that we have the correct number of decimal places. But nonetheless, we're going to get this. If we have that many molecules, then we read this. This is 108.06 grams per mole of molecules. And so we go 3.2 times 10 to the 24 moles of SF4. This is wrong too. What did they do? They screwed this up. Do you see how they screwed this up? What did they do here?
Yeah, moles. Oh, they cancel out moles and then.
Does this, look at this center conversion factor. Does this make any sense to you? It's like 1 ton is equivalent to 6 million trillion tons. That's what they're saying here. It makes absolutely no sense. When I see this middle conversion factor, it's ridiculous. It's wrong. How should I fix it? Tell me how I should fix that. Uh-huh. Yeah, we could do that. That would fix it, but look at what we're given. Are we given, is this the same as moles? No. And look at what they did. They said 3.2 times 10 to the 24 moles of molecules. It's like, okay, it's like, it would be equivalent to this, you know? It would be like, I want a dozen donuts. Well, give me a dozen 12 donuts. And so they give you a dozen donuts, which is 24 donuts. Well, this is, what they're doing here is the same thing. It's a mole Yeah.
So it says mole instead of molecule.
Yeah, a mole is not the same thing as a
Molecule.
molecule, and so that's what they screwed up there, so we gotta fix that. We'll do it next time. That's it.